Good afternoon, everyone. Hopefully you're all in the call or joining. I hope you're all keeping well and welcome to this Building Acoustics webinar. My name is George. I'm joined with Joanne as well. We're both the sales specialists from Svantek. We will shortly be starting the presentation, so I thought I'd give you a quick overview of what is going to be included and what we're going to be running through. So we will be discussing building acoustics fundamentals. We'll be going through measurements versus calculations and modeling, specific tests in more focus that you guys are probably already familiar with. And then we're going to go through how our sort of dual meter approach can help you guys save some time with building acoustics and sound insulation testing. So, and if you have any questions, make sure to send them to Svantek sales@svantek.co.uk. And we'll get back to you. So I will now pass you over to Adam, who is our regional sales manager from Svantek Poland, to start the presentation. So thank you.
Thank you very much for that, George. And do give me a thumbs up if you can see my screen, just so I can be sure. Thank you, Joanne. Thank you, George. All right, yes. So welcome everybody. Thank you very much for joining, taking the time off today in your afternoon to be with us here to talk a little bit about building acoustics. I figure I'd go ahead and introduce myself real quick. So my name is Adam Marczak, as George briefly introduced me. I work here at Svantek in Poland as a regional sales manager. So I am also involved with the UK office, trying to support them in the best way I can, making sure that they have the support they need from the factory. I have a background in acoustics, both in terms of previous work experience and my education. I hold a master's degree in applied acoustics from the Chalmers University of Technology in Gothenburg, Sweden. And I've previously briefly worked as a vibroacoustic engineer and acoustic consultant, doing some of the things that we've been talking about today. And just to give you a brief overview who we are, who Svantek is, for some of you that might not know exactly our history. So as a company, we've been established since 1990. We have a 40,000 square feet factory, or let's say HQ down here in the outskirts of Warsaw, where we do all our production in-house. The meters, instruments are being assembled by hand by our production department. The R&D engineers, the programmers, all of the competences that you need to be able to come up with a finished product with all the software and firmware that you will need for as an accompanying accessory. Those are all being created here in Poland. We focus solely on acoustics. We do not do any other fields like gas monitoring, dust, or meteo. We are focused and in the core a sound and vibration company. We have been since 30 years, and we've been really good at doing that. We hold several patents. Most recently, I would say our MEMS patented technology. We are the world's only holder of a PTB type approval of a class 1 noise monitoring station, the 307A, with a MEMS microphone. So very exciting times ahead. This is not what we want to talk about today. Today we're talking about the ins and outs of building acoustics. So just to give you a brief overview of what we're going to be talking about today, as George briefly did. So we're going to go through some building acoustic fundamentals, and the idea of this session today is not for you guys to learn how to do acoustics, not for you guys to be given some kind of insight into that, because one, we don't have time to do that. We don't have enough time in 1 hour to be able to cover all the pieces. Two, most of you, if not all of you, probably know this better than us, right? No, the idea of this, the aim of this webinar is to understand the scope of acoustic engineering, improve the general understanding of acoustic parameters, and for you to understand how we, as the manufacturer of a certain instrument that you then can apply in the field, how we think of different pitfalls, different solutions, different type of measurements, and we want to talk about those different approaches. So we're going to talk a little bit about building acoustic fundamentals, just so that we're all on the same page, just so we're all talking with using the same terminology, so that you can understand what I'm trying to convey to you. We're going to briefly touch upon the subject, why we even do in situ measurements, why we even have to perform a measurement in order to be able to clear a building in terms of acoustic insulation. And then finally, we're going to do the longest session where we're going to focusing on some tests. We're going to focus on insulation tests, on some reverberation time tests. We're going to go through the methodologies, go through how you perform that and what you do. So briefly, acoustic engineering, right? That's a word we hear here today. That's a word that you hear a lot. A lot of people wonder, what does that term really mean? Well, especially for all of you, probably being at the bar and telling you that, oh, I'm an acoustic engineer. Well, the first thing that pops into mind is like, oh, okay, so you're a sound designer, music designer. Well, I guess a lot of people fell for that. And initially, when they came into this business, they thought they were going to do music production. It's really not a lot of that, but it's still a very broad term that can cover a wide range of applications. So NVH within the automotive business, room acoustic, architectural acoustic designer doing big concert halls. That's also a classic. Building service noise, right? So HVAC systems, big systems on roofs, or building acoustic, as we said, public announcement systems, audiovisual design, environmental noise control. All of that really fits in within acoustic engineering. And everyone that says, well, I'm doing acoustic engineering, well, they're doing audiovisual system design, well, they're not wrong, they're still right. It just not within the scope of what we're covered today. And that's something I wanted to show with this slide today. So we're going to be focusing mainly on the building services. And what I mean by that is we're going to mainly be looking at insulation measurements, RT60 measurements, how to perform them, why to perform them, what the governing standards is, why we're going to do what we're going to do. We're not going to look too much at what we call architectural acoustics, right? We're not going to talk too much about that. I'm not going to talk about how to create the best room for the most enhanced acoustic experience, because in my mind that fits in within the room acoustic part of things, architectural acoustics, and maybe not what we're really looking at here today. So today we're just going to cover this in today's presentation, and starting with that, we'll talk a little bit about the fundamentals so that we're on the same page. So the first thing, we got to start real basic. What is sound? Well, it's sound. Sound is easy. Sound is something that we experience as a pressure fluctuation. So we have a static pressure in the air, and when we talk, as I do now, we put air particles into motion. So my vocal cords that I have here, they will now put the static pressure into motion. It will create a waveform that will then be picked up by our outer ear. That will then go into our inner ear, and in our inner ear we have small inner ear hair cells that will take that vibration that I just put the air into, and it will create an impulse that is then taken to our brain, interpreted as noise. So most commonly we use the term of decibels, or the value of decibels, to describe sound pressure level, and essentially it's a logarithmic scale. It's not easy to get into when you're new to acoustics. Once you start understanding the bits and of that, you can then start to understand the logarithmic scale before a little bit better. But essentially you have it right here in our presentation. The pressure that we measure, we need to have a reference. The reference is 20 micropascal. That is the threshold of hearing. So anything below that is going to be a negative decibel number. It still can happen, this is the human threshold of hearing. We can have negative levels, but as you can see here in the right lower corner, anything below that you will not be able to hear. 20 dB is super quiet. I don't know if I can hear that still as low level as that. 140 dB is the threshold of pain. After that, You can experience, acoustic trauma to your hearing. This is a very dangerous level of noise, and anything above 85, 90 dB is unwanted. So that's a little bit about the scale, that we're looking at. And in order to understand sound, in order to understand how we perceive it, we need to be able to talk about two things. We need to be able to talk about sound in time domain, and we need to be able to talk about sound in frequency domain. All right. So in this slide, we have two graphs, and they are showing the same signal. So we have a pure 250 hertz tone. A pure tone, if you're familiar with acoustics, a pure tone is what you're gonna get, for example, with an acoustic calibrator. Most commonly, it's gonna be at 1 kilohertz, and you're gonna hear a pure one frequency tone. Now, this is shown here in the time domain as a perfect waveform, where you can see here that, we see that we have what amplitude we have, amplitude of 1 or whatever. In this, we can just call it dimensionless. And you can see how perfect you see that the wave propagates. Now, if we would perform a Fourier transform of this signal, a Fourier transform being essentially a mathematical procedure to recalculate or re-represent time domain signal in frequency domain, we would have all the sound energy gathered at one frequency. And this is what is shown in the right hand graph right here. All the acoustic energy is at one frequency. Obviously, in real life, this does not happen unless using an acoustic calibrator. But this is just to show you, in normal circumstances, the time domain signal will not be as smooth and as beautiful as in this scenario, and this frequency domain will then be full of noise, full of different signals, because that's how a normal everyday signal looks like. But what I want to convey here is that we really need to pay attention to what is shown on the axis. So you have time here, you have frequency on the other one, and that is important when we look at acoustic things, and especially when we look at the next slide I have here in the presentation, to understand that there's a difference between time domain and frequency domain, and that one signal will look dramatically different within those within those two domains, but it will still be the same signal. We have now an understanding of the fact that a signal can be shown in terms of its time domain signal and a frequency domain signal. What I want to show with this slide is that we also have an amplitude value to add here. So amplitude will essentially assume or show us the magnitude of the wave, all right? In a very easy, simplified way, the higher the amplitude, the higher the volume. Or really, well, just to not skip too far ahead here, what I wanted to show with this slide is that amplitude in time domain, we're both looking in time domain here, right? Amplitude here will show us the magnitude of the signal, how loud, how high of a pressure fluctuation this is, right? And the denser the curves, that will show us a frequency information about that curve. So in the lower figure, we have a 1 hertz signal and a 10 hertz signal, both being represented in one domain, in one graph. And you can see that the 10 hertz signal will do 10 repetitions in the same time as 1 hertz signal. So that kind of tells us, well, we can have varying amplitudes, we can have varying frequencies. So how do we perceive sound? Because that's essentially what we really have to focus on. Well, human perception of sound is not as easy as you might think. So just because something is 100 dB doesn't essentially need to mean that we're going to perceive it always as 100 dB. This is why we have different techniques to try to help to show how us as humans, how we will perceive the sound, all right? The most simple way is A weighting. So what you see here is 3 types of weighting curves. And what I want to show here is the first signal here on the curve, on the red curve, the 94 dB pure 250 hertz signal. All right, what do I mean by that? All right, so assume you have a calibrator. Assume you have a calibrator that can switch between two frequencies. It can switch between 250 hertz and 1 kilohertz. All right, when you turn it on, it will say 94 dB. You would put it close to your ear and you will say that's not 94 dB because the 1 kilohertz tone that I just played before with the 94 dB signal was much louder. And that is essentially the introduction to psychoacoustics, our human perception of sound. All right, just because the amplitude of that signal is the same as the signal of 1 kilohertz doesn't mean that we as humans would perceive it as loud. Okay, so we as humans, if we apply the dBA curve here as shown on the picture, we will perceive the 94 dB tone as 86.4 dBA. And I will tell you in a bit how that relates in terms of our perception of noise. While the 94 dB tone at 1 kilohertz, as you can see on the curve, is lying perfectly on the 0 mark, so it's not amplified nor is it damped, we will perceive that as 94 dBA. So the pressure fluctuation for the 250 hertz tone and the 1 kilohertz tone is the same. However, the perceived noise level is different. And this is shown in a very basic form, and believe me, this is basic. Human psychoacoustics is a whole huge field within the business segment, but also within the academia. And this is the easiest way to kind of show how we perceive different sounds, because our hearing is frequency dependent. For years and years, thousands of years of evolution, our people that were here before us, somehow the ones that could hear tones better at 630 hertz to, I guess, 10 kilohertz, they had a better chance of survival than the ones that could not hear those frequencies as well. So this is basically to show you that we can have a tone of the same amplitude that will be perceived at a different level. Another way of showing that is through NC on noise criterion or noise rating curves. So this is also similar to A weighting, where we are trying to take into account the human sensitivity of hearing, and essentially you will have this requirement. NC curves you'll often see in the US, and noise rating curves may be more commonly used in Europe. You will see this requirement, especially when it comes to mechanical noise sources. So you know, ventilation, or I don't know, some big AC in the room, and you will have, as you can see here on the table, you will have a certain NR level, right? NR level as, for example, private dwellings. NR 30 should not be over. Should not be higher than NR 30, and it's very easy to use these noise rating curves because essentially you will put a third octave band or octave band spectrum over this, and whichever curve is the highest that overlaps with one of the octave band's bars, well, that is our NR rating. So the lower the better, the lower the background noise, but that's also another one that shows you that we can't just purely look at the dB value. We must be aware of the fact that our human hearing is perceiving different frequencies differently. And I'm gonna switch back real quick here. So again, you see here 86.4 dBA at 250 hertz, 94 dBA at 1 kilohertz. So that is, if my math is not off, approximately an 8 dB difference. So what does that mean? This slide is the last slide of the acoustic fundamentals, but I think it's a very important one for people that are new to the perception of, people that are new to the use of the logarithmic scale using dB levels. So 1 to 2 dB on paper can look like a lot, right? Well, it's a 2 dB difference. But in terms of hearing, if I would now lower my voice with 2 dBs, if I could do that somehow, because if I had the magic ability to control the sound pressure level of my voice, you would not be able to hear it. It's first around a 3-4 dB change where you start to notice something, where you start to notice that I'm either speaking more loud or less loud. And with 5 to 7 dB, there's a noticeable change, and around 10 dB, that's where you perceive that I'm speaking twice as loud, right? So if I'm going to calm my voice now a little bit and then increase it like this, well, that's a 10 dB difference when you perceive it as a doubling of sound. So again, going back to this slide right here, 86 to 94, same amplitude, but perceived almost twice as loud as, so 250 hertz is going to be perceived, or 1 kilohertz is going to be perceived twice as loud as 250 hertz, even though it's the same pressure, it's the same amplitude. All that differs is the frequency. All right, so we have covered that now. We can move on to building acoustic fundamentals, and bear with me here a little bit more. We're going to go through some basic terminology, some basic fundamental concepts, and then we're going to move on to the more interesting part of this. As I mentioned in the beginning of this presentation, we're going to be focusing a lot on partitions, sound insulation, these kind of things. So a general concept when we're talking about building acoustics is lifted here, all right? Sound reduction of a partition. So you can see here that sound reduction is going to be denoted by R, and it's a logarithmic value of the sound power incident on the wall, all right, on the wall, and sound power transmitted through the wall, okay? That's gonna give us our sound reduction. And this is the most fundamental approach that we're going to be talking about, because we need to understand how the people who created the whole business of building acoustic, how they thought of the process. And it's essentially a very easy process. You compare something inside a sending room where there is a lot of noise to a receiving room where there's little noise, and you look at what was the power, sound power on the wall that was sending versus on the wall that was receiving on the outside, and that will give you the information about the reduction of that wall. But we have now introduced a new term here, sound power. So what is sound power? I think that is very important to know, and that is very important to remember, that there's something called sound power level and there's something called sound pressure level. So maybe you use a lawnmower or I don't know, I guess a leaf blower or something like that, that will have one of these two markings embedded somewhere on a sticker or somewhere else. And if you're an acoustician and you've worked a little bit in web acoustics, these can tend to cause a lot of annoyance, especially if you have the one here on the right, LPA 89. So what this will tell you is L stands for level, and P, I guess, for pressure, and A stands for A weighted. So we've already covered what A weighting is. But what we don't know is essentially how this was measured. What was the standard? How far away from the noise source this measurement was obtained. And then we have on our left-hand side, we have the LWA, all right? And this stands for sound power level. And sound power level is something different. Sound power level, when I see this, then I understand, all right, 60 dB, that is the sound power level. That is the effect of sound being transmitted by this machine. And the easiest way to understand this is using the heat analogy. So in this icon that we have here, we have a radiator inside of a house, right? The radiator has a constant power generation, right, in watts. So it generates the same amount of heat no matter what, all right? Let's just assume that for the simplicity of this example. Well, the measured temperature is going to be changing depending on how close I am to this radiator. Let's assume that we're in a free field scenario and that the only thing generating heat in this room is that radiator, and the further away you're from the radiator, the colder it gets, because it just maybe a fire would be a better example, open in an open field. But this is for you to understand the difference. So a sound power level here is telling you how hot is this particular radiator. The sound pressure level, however, this is the local value. So we have person number 1 and person number 2 here holding a thermometer, and they are measuring a temperature inside of the room, the same way that you could be measuring a sound pressure level inside the room, and they both have different levels. They are both right, because the one most to the left is holding his thermometer and he's reading 25 Celsius, while the one closest to radiator is reading 30 Celsius, while the sound or the power level at the radiator is 35 Celsius. Everyone is right here, but this is what we need to understand. And this is why a sticker like this can bother you, because the LPA level 89 dBA, I do not know, was that measured 1 meter away from the device? Was that measured 2 meters away from above, from the side, in an anechoic chamber? How was the measurement performed? I have no clue. However, if I have a sound power level and I need to do an analysis or do a model of how much noise, what would be the background noise of this room that I have right here, that I have all the data on, I know exactly how much it's absorbing, I know its geometry, I know its volume, how much would the background noise go up if I have a sound source with a sound power of 60 dB? Well, in that case, I can easily use all the mathematical formulas that I have for air absorption, etc., to understand how much noise propagation I would have in that room, how much noise I would come to. So this is a very important notation that we need to have under our control. And finally, the governing standards. So I think it's very, very important to know that the building acoustic sector of our business is well defined. There are a lot of other niches, segments of this business that are not as well defined, I would say, especially in the vibration sphere of things, but that does not go for building acoustics. Building acoustics had a classic standard in the ISO 140 that was implemented into the acoustic industry back in '97, and many legal requirements were then connected to the standard. But 16 years later, after that, it was found that a lot of things were lacking, missing. It was not always ready for everything. So a new standard was generated, the ISO 16283, and that was the one that is most commonly used nowadays in this business. That one introduced new techniques, such as the scanning technique, the 8 or whatever we see right here, the rubber ball impact test, and many more, which simplified the approach, which simplified this methodology to measure. Both are still being used today, and if you're using Svantek equipment and you have our BA Assistant app, you can still use the ISO 140 standard or the ISO 16283, but I would say that 16283 is the one that is most commonly used, that you will see in most countries, and that most country regulations will be based on. Then we have another very important ISO standard, which is the ISO 717, and this is not a measurement standard. It does not take care of the methodology of measurement. It does not specify to you what kind of measurement equipment you should use. No, it tells you how to take the data you've been given and calculate a reference level that we can all look at and understand, that we can all use as a benchmark, as a threshold, and that we can then compare against each other. So it essentially tells us how to calculate numerically a weighted value to express the acoustic performance of an element as a single value. So that's what the ISO 717 does, and they're all split up in parts. So ISO 717-1 will talk about airborne sound insulation. ISO 717-2 will talk about impact. and so on and so on. And it's important to remember that the standard does not define if something is good or bad. It just tells us how we should be performing the measurement. And depending on where you're listening from today, there will be different local regulation. There will be a different local regulation that will tell you if this is acceptable, if this passes or not. What the standard does tell you is setting a strict instrumentation requirement. All right, so for building acoustic, you always have to have a ESE 61672 class 1 instrument. You cannot be using class 2 or type 2 instruments for most of the tests. A calibrated device is needed because cases like this can end up in court or in disputes. So this is why you need to have the top shelf stuff. You need to have the best equipment available on the market. So as I mentioned, calculations versus measurements. So why do we do them, and what do I mean by that? So as you can see here, nowadays we have a lot of modeling softwares. I mean, BIM-based, Bastian, Insul, all of these modeling softwares where you can do very complex structures, very complex systems, where you have a double leaf wall with partition or whatever, and that will give you even a graph where you have the reduction value versus frequency. As you can see on the picture right here, it will tell you where the where the coincidence point is. It will tell you what to expect. So why do we still need to do an in situ measurement and on-site measurement, which is both expensive, time-consuming, and essentially a very bulky process where you really need to know what you're doing? Well, it's for the same reason as we do bridge load tests when we have a very good bridge model. Until something is tested, we can't really promise that it works, right? Because it all goes down to the quality of execution. So here's an example that you could do a great model in Insul and tell somebody, well, we'll put this duct here and we'll have this RW70 wall, and that's gonna do great things, so you don't have to worry about anything. They won't be able to hear you. We have placed some silencers on the duct system, everything will be fine. But when you arrive on site and you see something that we see here on the left, where there's a visible hole, you can have as strong as a wall you want, but the weakest link will always be the one that will completely kill the acoustic insulation of that entire wall. So it is the same as with heat, right? You can have a very insulated wall, and if there is a hole in that wall, a lot of that heat will escape anyway, and I think in acoustics it's even less forgiving. Same goes for floating floor setups where one person can just punch through it and destroy the damping of the floating floor setup. So you need to be able to check all of these unsealed penetration sources. You need to be able to perform that test before, because no matter how good of a model you do, if there's a lot of flanking, if there's a lot of unsealed leakage, you will not get the level that you're expecting. And same, what I want to show with this is the difference. So you could go here and you have your green wall, which you have models for 53 dB RW, but in reality when you come there to site, it's only 40 dB, right? Because there is leakage, there's flanking, there are different things. We'll just cover in a bit the difference between RW and DW or DNT and stuff like that. So this show you that we really need to be able to perform these tests. And one of the first tests that you will do as an acoustic consultant is airborne sound insulation. So airborne sound insulation, the concept is fairly easy and understandable. So you will have one partition under test. In our example here, the partition that is under test is the purple wall with the white door on it. You have a receiving meter inside the receiving room, which is measuring constantly it's measuring the noise level within that room, and then you have one inside of the sending room. we are assuming that we have a diffuse setup, so we're going to try to diffuse sound field. So what we're going to try to do is to have as many average as possible. Then you can do different types of levels, as we mentioned in the previous slide. There's a D&T value, for example, or an RW value. So an RW value relates to a laboratory rated sound reduction index. So perhaps some of you have been to these kind of laboratories where they have a setup room with super heavy walls, and you only perform a test on one single element. You perform a test in the laboratory, and that gives the wall performance without any flanking path. So that would only work in a real life scenario in a very good building where we have very high mass walls surrounding your construction. So if you're measuring up an RW value for again, going back to this example, for a wall here, and you're saying, well, this wall is going to be, let's use the green wall again, this wall is 53 dB RW, so you don't have to worry about anything. Well, you still have to worry about the fact that when you're there on site and you start adding your flanking transmissions, you start to have flanking through ducts, through connections between joists, through doors and windows that are not necessarily on that wall, you're going to have a completely different value. So that's the difference. The D&T value is the one that you will most likely use in a real life scenario when you try to measure this. So maybe not skip too fast. You're going to perform a measurement inside the sending room, and you're going to perform a measurement inside the receiving room. Or if you have the dual building acoustic kit from Svantek UK, you will be able to do both at the same time, saving yourself time and also raising the reliability of the result that you get. And then essentially, if you're doing a D&T measurement, you're going to be subtracting this sound pressure level in the source room versus the sound pressure level in the receiving room, and on that you're going to be adding a correction for the reverberation time in the receiving room. So you're going to have to perform at least 3 types of tests, and in order to assume a good average, to assume that we are working with diffuse field, you need to perform these tests in many locations in the same room, using the same sound source, and then preferably moving that sound source. Once you have gathered all of that data in third octave bands, that's when you get the D&T value. Well, the D&T value is going to then be in the form of a curve on this, in this one shown as the blue curve right here. So then again, we're going back to ISO 717. You want to have one single value to define the performance of that partition in that project, in that room, in that building, right? So we're looking at the on-field measurement. We're not looking at a laboratory level. So how do we do that? Well, you have a reference curve defined by ISO 717. So you really need to have the standard in front of yourself. You need to have yourself an Excel sheet, or as you can, if you do this using our BA Assistant app or our Svantek BA extension, then you will be able to have all of that already in the software. But what you need to do is start shifting that curve step by step. So you shift that curve till the sound reduction curve. It's a little bit tricky to explain, but essentially what you want to do is you want to shift that reference curve by steps of 1 dB till the sum of the deviations is not larger but as close as possible to 32 dB. So anything under here is going to be summed up, and when that sum is 32 dB, that's when you stop the reference curve. And this is also shown in this picture right here. The dotted line is the initial position of that reference curve, and the solid line is the new position of the reference curve. And how do we get the signal value? Well, we look at where we are at 500 Hertz for that value, for that reference curve. So we're looking at the reference curve. We don't care anymore about what we measured up. That is our D&T weighted value per ISO 717, okay? And for airborne sound insulation, the higher the D&T W value or the RW value, the better the acoustic insulation performance, okay? So we wanna go as high as possible because that's the best possible solution right here. And on top of that, to make it a little bit more complicated, we have to add correction coefficients. So a lot of regulation will require you to take into account something they call spectrum adaptation term. So you gotta remember that when you're performing this measurement, as shown in this picture right here, you will be using an omnidirectional source, you know, like a dodic or whatever you call them, from whichever manufacturer that does a good job of generating a very strong pink noise signal that is going to be giving good level of energy on all the frequencies of interest. So that is not really going to give you the exact noise source that you will expect in a normal scenario. I mean, you're not expecting your neighbor to be blasting pink noise in the middle of the night through his omnidirectional speaker. You're going to be experiencing different types of noise sources, right? So because of that, we have a spectrum adaptation term, and that is also covered by ISO 717, which recommends which spectrum adaptation term to apply to a certain noise source. So if you're measuring the insulation of a building that is close to, I don't know, urban road traffic, then you might want to use the CTR correction, and the CTR correction will ensure that low frequency sound is adequate in the construction, that damping is adequate, and that we did a good job. And to understand the differences, then I think this slide will help you to understand differences between the different levels. So if we take an RW value plus CTR, and we have a 40 dB value there, all right? So you've made your measurement, you calculated it, and it ended up being 40 dB. That's your answer, 40 dB. Then if somebody in the room next to yours, behind that partition that is rated at 40 dB, speaks in a normal tone, it will be audible for you and will cause annoyance. Same, loud talking, very audible, screaming, music. So you can follow this graph here and follow the understanding, you know, 45 dB, well, still not great. And this is why generally a level above 50 is considered to be okay between dwellings. So when you're doing these measurements and you have something above or 50, you're usually okay-ish, but it's again dependent on the local regulation. It's dependent on the sound design plan, how you want to do it in your particular building. You gotta understand the need of the client, you gotta understand your local regulations, and based on that you have to apply a solution that will work. But until you have performed an in situ measurement on site in that field, being in that room where you did that project, you cannot really rubber stamp that and say, well, it works, because as we mentioned before, the model is not the same as the in-field measurement. Airborne transmission is tricky. I mean, as we mentioned before, transmissions via weak links, if you overly define a wall, create a super wall, 75 dB RW, and you're like, this is going to work, but you forgot that you have huge heritage windows on your in both rooms, all the sound will be traveling through those two windows and you will have leakage. Same goes for leakage between joints or ventilation ducts. A ventilation duct is a perfect example of something that can lead sound, or even pipes and stuff like that. Leaking doors is very common. So you as an acoustician being on site, you gotta play detective sometimes. You gotta walk around, listen for noises. Is this a high frequency noise? Well, that indicates maybe leaking through the windows. Can you, for example, put your foot on the door, hold it tightly? Will you get a different result? That is part of the job. That is part of why we sometimes can sell acoustic cameras, because it enhances the ability to see that, to visualize that. But sometimes all you need is to have a device that can show you the third octave band spectrum, or a very trained ear. I mean, I've worked with acousticians that have been in this racket for years and years, and they can just listen, they can just hear it. and they know how to perform it. So these are some of the tricky parts when it comes to airborne transmission. What can go wrong, how it can go wrong. Installation noise, it's a problem. But you gotta measure it, and you gotta always pick the weakest rooms when you do that. In Sweden, where I worked, we usually would go, and if we had an entire building, we had to make a selection. You know, we have a building with 150 dwellings, and God knows how many partitions. So you gotta make a choice where you go, and you go where you are expecting it to be the worst, based on your experience, based on what you've seen in the past. And you need to do a reliable measurement. And yes, with the ISO, with the new ISO, we have seen a lot of scanning. Instead of doing discrete points, we have seen scanning of the microphone. That is a technique that requires some skill. You got to remember that the sound level meter is class 1, but not if you're holding it like this, all right? Because then you are introducing the reflection from your body. All right, these instruments have been certified as class 1 instruments because we make a correction for the reflection coefficient. If you are holding it close to your body will introduce a reflection that will then decrease the reliability of your results. Therefore, if you perform these scanning aids or scanning techniques, you gotta really make sure that it's far away from your body, that you're holding it, and that you're not moving it too fast. A way to increase the reliability while cutting down on the time is using the dual approach. Being able to measure in the sending and receiving room at the same time is a great asset, and we've seen some countries where this is becoming a norm. In Asia, they are requiring to do this for laboratory level measurements, but we are seeing more and more approach where simultaneous measurements are not only good for the saving of time, but also for the reliability, because they can both then measure the same artifact that you might be able to miss if you're performing measurements in a consecutive manner. So that was a little bit about airborne noise. Now we'll move on to structure-borne noise. What is structure-borne noise? So structure-borne noise is interesting. Easiest way to just introduce anyone to that is this is noise that is most often being made by somebody running around or dragging things across the room, and you will perceive this most likely if you're the neighbor underneath that person, but in a lot of scenarios also if you're in the room next to that person or next to that noise generating room, can be very annoying and a very problematic thing when you're designing gyms where you have high impacts and a hard time to be able to damp them. So the interesting thing about structure-borne noise is that it can actually be more intrusive and problematic for the person on the receiving end than on the sending end, in terms that it will actually make more noise to the receiver than to the sender. That is often because the structure-borne noise, let's say again from somebody tapping on the floor, that will be transferred through the different partitions through those leaves, and those will then start acting as loudspeakers, almost vibrating in the same way as they were excited, and then putting into motion the air particles around it. Same example as I used in the beginning of this session, with my voice exciting different types of chords and making the air move around, and we perceive that as noise. Well, the same goes for the walls. So structure-borne insulation approach is very similar to the airborne. We're again measuring in this sense only in the room, in the sending room. I'm sorry, in the receiving room, of course. So in this scenario here, you have yourself a tapping machine. You can also use an impact ball, and you will start pounding on the floor, and you need to measure that in the room. Therefore, it is the other way around from airborne insulation. The lower the LNT value is, the better for us. Okay, so this is something that is important to remember. And in situ measurements are needed. Diffuse sound field is needed. Therefore, as you can see here on this on this slide, I've added a lot of devices, but this is just to show you that you should be using a lot of measurement positions. You should be having a lot of sending positions. You should avoid placing tapping machine along floor joints. So you should not be placing them between them, but rather on the 45-degree angle. Avoid placing that too close to heavy objects, too close to big furniture objects or walls. Ensure an even spread. And if flooring is sensitive, and that does happen, we've seen that from own experience, you do not want to put the tapping machine on the tile floor sometimes, especially if those are expensive tiles that have not yet been properly attached to the floor, because the tapping machine, although it is supposed to not break a floor, it can do some of that sometimes when you are in the when you're unlucky. Therefore, we also have this impact ball here at Svantek, which you can use for sensitive floorings, and this is fully compatible with the BA Assistant app in order to be able to receive a good result from that as well. There is an ISO covering that as well. So just switching back to this slide, as you can see here again, the T right here stands for reverberation time, and that is an entry to the next part of the presentation, which is on reverberation time. So again, when you perform a measurement like this one, you should perform the measurement at least 2 measurement positions in the sending room. So put it in 2 positions to be able to have a good average, or more if you want. And then you should have a couple of measurement positions in the receiving room. But at that point, you're not done yet, because if you want to be able to get that LNT value that you're so desperately searching for, you need to also be able to measure the reverberation time inside of the receiving room. And in the next part here, we're going to cover what reverberation time is and how to measure it correctly. So reverberation time is one of the most fundamental ways to describe a room from an acoustic perspective. All right, so the room acoustic business is also huge. Again, going back to our initial slides, where we're talking about the ability to be an architectural acoustician, where you're doing big music halls, big concert halls. Well, essentially we're looking at reverberation time, and reverberation time is going to then be used to get other metrics like clarity, strength, etc. Right? But reverberation time is going to be fully dependent on the volume, geometry, and the absorption factor of the room. So the more absorption you have, the lower the reverberation time is going to be. This can probably be seen a lot in if you ever moved apartments, you get used to the soundscape of your living room, but then when you remove the carpets, when you remove the sofa, when you remove the drapes and all of the other things, the same room suddenly sounds much bigger because the reverberation time has gone up. And here's 2 contradictory examples. So you have an anechoic chamber with full absorption, and then you have a reverberation chamber where this room will be small but will in fact feel like a super big room. And you need to measure these in order to be able to get LNT and DNT values, because you need to normalize for the reverberation of the receiving room, because you want to make sure that the room that the noise is not being amplified by the room even further. It's rather being absorbed and kind of kills the noise being sent into the room. And we need to make sure that this works. This is done in accordance to ISO 3382 and requires octave band analysis, and can be obtained both using an impulse or decay method. I think the decay method is to be recommended. This one is the method that you use when you have a sound source and you cut the noise, and while the impulse noise is just creating high impulse, maybe not by a clap of a hand, but maybe blowing up a balloon or a gunshot or so on. And the last test I want to talk about is STIPA. STIPA stands for speech transmission index for public address systems, and it's essentially a metric that tells you how well you can hear or understand the different things that are being said. So one example of application of STIPA is to our cruise ships. In cruise ships, you will have people sleeping in a place where they are not used to be sleeping in, same as in hotels, but with cruise ship, as we all seen Titanic, it's extra dangerous. So all rooms need to be equipped with a public address system where they will address the people and tell them what to do in the case of an emergency. Well, in order for that public address system to have any validity, to have any real sense, it must also have the ability to be, for the person to even understand what is being said. And that can be measured using Svantek equipment, that can be measured using our app. There's an algorithm for it, and you will need to have a talk sound source. So you will play then a reference signal within the sound source, whether that is a public address system or a talk box that you place in a classroom. And you will then measure that noise, you will measure that signal, and the application and the device will then tell you how that sound was modulated by the room, whether it was good or bad. And the metric is really easy. It goes from 0 to 1, with 1 being excellent and 0 being terrible. And there are different countries where different regulations are put on the STI, for example, for hotels, for cruise ships, but also for classrooms, for rooms, for speeches, an important parameter. With 2 minutes due, I now leave the floor to you again, George. So thank you very much for your attention. I hope this has been of some use to you. And if you have any questions to me or to George, you can pass them on sales@svantek.co.uk.
Yeah, thank you very much, Adam. That was great. As Adam mentioned, if you do have any questions, make sure to send them over to sales@Svantek. Hoping you guys have found the presentation useful, and we will hopefully catch you at the next one.